Okay, let's do parametric forms.
In case he forgot the other day. Except we did a lot more.
All right, what the heck are parametric forms? That's when the relationship between two variables, x and y, is expressed in terms of a third variable called a parameter. For example, if you have y equals x squared, that's how we traditionally define a relationship between y and x. And we can do the graph of this, y equals x squared, which is the set of ordered pairs in the plane that make this equation true. And we get our familiar parabola. And this is a static set of points. It's a set of ordered pairs, okay? It's all the ordered pairs in the plane where y is equal to x squared. There's no sense of direction here or movement, okay? We can impose that on that relationship by expressing it in terms of another variable called the parameter. In other words, what we may do is change this into this. Let x equal t and y equal t squared. Now, what we get here will be the same set of points. But if we do this in terms of increasing the parameter, let's say t starts at -3, x will be -3, y will be 9. When t is -2, x is -2, y is 4. When t is -1, here, this would be -3, 9. This would be -2, 4. We're going to get the same set of ordered pairs, but there's a movement implied, a direction. It's called an orientation. When t is -1, x is -1, y is 1. When t is 0, x and y are both 0. And then t is 1, we get 1 for x and 1 for y. And when it's 2, we get 2 for x and 4 for y. And I might as well complete it. 3 for x, we'll get 3 for t, gives us x equals 3 and y equals 9. We'll get this parabola all right, but there's an orientation. As we increase the parameter, a particle following this path would start here in the upper left, move down, and go to the upper right. That's its orientation, left to right orientation.
Is there right to left?
What's that?
Is there right to left?
No, this is left to right. Left to right.
No, I'm saying, is there?
Oh, yeah. Good question. Can someone give me a way of defining x and y in terms of a parameter so we get the same set of ordered pairs, but the orientation is now right to left? Can someone think of a way of doing that so the orientation, in terms of increasing the parameter, will give us an orientation of right to left?
X equals -t.
Perfect. X equals the opposite of t, or a -t, and y is equal to t squared. If you do it this way, watch what happens. Let's start t at 3 like we did before, at -3, which we did before. When t was -3, x was -3, and y is equal to 9. And we got this point to start with. Now if t is -3, x is equal to the opposite of that, 3, and y is still 9. So it starts us over here, okay? At this point, 3, 9. And now when t is -2, the x will be a +2, take its opposite, and the y will be a 4. And then when t is equal to -1, x is 1, y is equal to 1, 0 gives us 0. I'm off a little bit of my drawing here. And what will happen is we'll get the same set of ordered pairs, but a totally different orientation. We'll get the orientation that's right to left. Okay? Good call. Excellent. But there's more to it than that. Okay? By using this parameter, not only do we get an orientation, but we get velocities, okay? There's no velocity in going around that set of ordered pairs. It's static. We have a velocity now. Right, let's go back to the first one here. We can find out how fast x is changing and how fast y is changing in this parametrically defined relationship between x and y. We can find dx dt. That's how fast x is changing with respect to t. Dx dt would be 1. Well, it's constant change of 1. X is always changing 1 unit per change in t. But what about the y? The y is changing 2t. Okay? It's not a constant. At t equals 3, say, we have an x velocity of 1, and we have a y velocity of 6. And what we're going to do, not this chapter, but the next chapter when we talk about vector valued functions, we'll talk about a velocity in the x direction, and we can represent that with a vector. Okay, we can have a vector in the x direction, and we have a vector in the y direction. And at 3, this will be 6, and this will be equal to 1. And we have those two representative velocities, one in the x direction, one in the y direction. Okay? So, as we move around this, we'll have different velocity as well. So there's two advantages to using a third variable to define the relationship. One, we get an orientation, and two, we get individual velocities, okay? Now, given the individual velocities, can we turn around and find dy dx, the slope of the tangent line? You okay, Dylan? You want to get a drink? You sure? Teddy, you ready to do mouth-to-mouth on him or what? No, you're not ready?
I can't. I'm sorry. I mean, I like Dylan and stuff, but not like
Not like that. All right, okay.
I think I swallowed wrong or something.
All right. Well, if you need to get a drink, go get a drink, all right? All right. Okay. Here's the deal. You're going to be given an x and y in terms of a parameter. You're going to be asked for orientation, and what you do is generally start the parameter at some number and increase it. Start it at 0 and increase it to find the orientation. You may be asked to find the dx dt, the velocity in the x direction, velocity in the y direction. Okay. You may also be asked to find the slope of the tangent line, which is still dy dx. Well, let's see. How can we find dy dx? There are two ways to find dy dx if we're given x and y in terms of a parameter. What would be one way? Suppose you had to find dy dx here. What could you do?
Multiply by the inverse of dx by dt. Like dy by dx, dy by dt times dt by dx.
Yeah, wow. Use the chain rule. Wow. Pretty good. What'd you do? Take this course already or what? No? Wow. All right. Well, one way to do this would be to find dy dt, find dx dt, and this is a variation of the chain rule. Okay? dy dt is 2t. dx dt is 1. dy dx would be 2t. So at a given value of t, let's say t equals 3, we have our point 39, and we have the slope of the tangent line would be 6 at that point. Okay, that would be the slope of this tangent line. That slope would be 6. That's one way to do it. It works out pretty well. What's another way to find dy dx if you're given x and y in terms of t?
Can I use your keys?
Sure. Check out this glass, huh? What's that?
Too much testosterone.
Yeah, that's what they said too. Yeah, and we couldn't even get anybody to give Dylan a mouth-to-mouth when he was joking here because we just couldn't know it. Nobody would do it.
I can die, it's all right.
Did you recruit him for the math team?
Oh, the math team. Good call, Gene. All right, here we go. Let me talk about this for a second. Not this Monday, because we got a department meeting. Today we got a faculty meeting. Wednesday we had a division meeting. Holy moly. But anyhow, a week from Monday, we're going to start math team practice. Oh, what happened?
This doesn't have the key I need. I'm looking for the key that will unlock the math meetings. Do you have that in your desk or something?
Ooh, yeah, yes, yes. They're in my desk.
I can wait till you come back.
Okay, and one of those drawers there, there's a pack. Okay. All right. Math team. Okay. We do have a math team here at STCC, and we have a pretty successful math team here at STCC. And what it does is meets on Monday afternoons at 12:15, where we have pizza, free pizza, and we do math problems. Okay. Twice a year, once in the fall, once in the spring, we compete. What does that mean? That means that on those times, we get a test, an exam, 20-question exam from the Atlantic Regional Math League. We pass it out. You have 1 hour to do the test. Pass it in. We correct it. We send in our top 5 scores. That's our team score. And this Atlantic Regional Math League. Actually, now they have teams from all over the country. All 2-year community colleges compete on this math league. There are prizes. If you're the top scorer in the 2 tests for STCC, you win $100. If you're the second place scorer, $50. Third place scorer, $25. Like I said, we do well. In New England last year, I think we were about 6th in New England last year. 1 year, 2, 3 years ago now, we were number 1 in the Northeast, all right, which includes New York State. Really awesome team. We've had good teams recently. We haven't repeated as Northeast champ
Let's do it. This is the year.
Could be. The only problem with this year is we have no returning students. We have you didn't compete last year at all, did you? Yeah, no. So we have no repeating students. Danny Glassman for the last 3 years in a row or so has been a top scorer. What's that?
The kid's a machine.
Yeah, he's good. He's really good. Yeah, Glassman's great. We've had some great students come through here and do really well on Glassman last year, I think, was number 2 in New England. We've had a student at number 1 on our math team. So, I mean, you compete, you do math problems, you learn some math. They're pre-calculus problems, there's no calculus problems, but they're interesting problems, they're different problems. If you run a math league team in high school or so, it's that kind of problem where you don't generally get, and you have to use your brains and you have to do a creative kind of thing often, right? I can give you an example. I'll give you an example. This is one of my favorites.
Just
Everyone
sitting
just
here
join the math
recording
team.
the screen just sitting there.
The viewers won't mind. They like this kind of stuff. Maybe you could like
But they're already
tilt
hearing
it.
that
and you
interrupt.
could,
It's recorded.
How do I?
How do you turn it off? How do you pause? You don't pause it. You can just,
I hit record.
yes.
Okay.